Hello everyone. Just wait for some time for others to join in and then we'll start. Hi Rohit.
Hello.
Okay. I think in the interest of time, let's get started. So today we will look into one more classification algorithm that is related to probability. So a lot of probability will be involved, especially conditional probability will be involved. We will take a use case related to credit cards or the defaults that happens in the credit cards. Before we get into that, let's just try to finish what are my basics that I need to know with respect to knife base. Right? So let's just try to write some notes on it. Okay, so first of all, it is a classification algorithm, right? Which is used for both binary and multi-class use cases, right? However, the backbone of this algorithm is basis conditional probability, right? Now, there is an advantage, there is a disadvantage of the fact that it is based on conditional probability. So I'm going to write as point number 3 and 4, uh, uh, which I can say as per point number 2, we can say that the model's computation, okay, computation will be relatively much faster as compared to others, right? We'll come to know why when we look into what is Bayes' theorem and what is conditional probability and so on. It is basis conditional probability, and I can say uses a very simple or ordinary implementation of naive Bayes of Bayesian of Bayes' theorem. Why it is called naive Bayes? I will also explain that. Right, that will not be an issue. Once we go ahead, we will explain why it is called naive Bayes. But we must note that because it is based on probability, usually the calculations of probability are very simple. And that's the reason why it doesn't take much time to calculate the probabilities. Because probabilities are basically at max, we will be doing multiplications and divisions, right? We may also be doing some kind of additions from time to time. So other than basic, very, very basic mathematics, you don't need anything else to describe what is happening probabilistically, right? That's the reason why this model is very fast, right? Compared to any other models, this is really very fast. But there are some issues with this model, which I can say in point number 4 also. So as per point number 2, because it it is a naive implementation of Bayes theorem, it assumes assumes no multicollinearity within the data, right? So whatsoever use cases we may have, that use case has to be, or the data has to be, or uh, its concentration has to be, or the way we prepare the data has to be such that we don't see any issues with multicollinearity. Because if we have intercorrelated features, okay, then naive Bayes will not work. Okay, naive Bayes works on that basic assumption only that there are, let's say, very, very simple thing, two events, and two events are completely independent of each other. And that gives us the basics or the basic idea behind Bayes' theorem. So let's just quickly define Bayes' theorem, then we'll write its function also. So Bayes' theorem is basically a probability theorem which comes into conditional probability. So when we talk about conditional probability, we make use of Bayes theorem. Now, knife Bayes does not use the entire concepts of Bayes theorem. It uses the background. It uses as is the skeleton. However, it also makes that assumption that if I have features f1, f2 until f of n in my data, then each and every of these features are independent, or these events which are occurring, okay, they are mutually exclusive and they are independent. There is no interrelationship between f1 and f2 in the sense that the happening of f1 does not impact the happening on f2 in any case. So this line should not be there, right? So there is no relationship between f1 and f2, right? Now, let's say if I have a data set, just to clarify this point, if I have a data set which is the weather data, which we looked into when we were learning, let's say, decision tree using that Excel sheet. We saw there was one column related to, let's say, Outlook. Okay? We had an Outlook column, we had a temperature column, we had a wind column, and we had a rain column, right? Now, obviously, if for some values of Outlook, let's say it is sunny, okay, if Outlook is sunny, obviously the temperature is going to be high, right? I mean, there is a very high chance, or there is a very high chance that if the outlook outside is sunny, we have a sunny weather, the temperature may well be very high, which means if not for the entire data set or if not for all the observations, at least for some of the observations, there is a good relationship or there is somewhat relationship between outlook and the temperature field, which should not be the case. This should never be the case. If this is the case with my data, then naive Bayes is not going to work. Okay, naive Bayes is not going to work. Now, unlike KNN, this can only be used in case of a classification problem because of the way it is structured. So let's try to define what Bayes theorem is saying. So what Bayes theorem is saying is that any events probability, which we already know. So how do we define the probability of events? We define probability of events like P of A, let's say. So there's some event which is happening, which is A. I give the probability of events as the total number of favorable outcomes, right? Divided by the total number of outcomes, right? So if I am playing with a dice and I'm rolling it 6 times, right? Out of 6 times, only one time I got 2, or 2 times I got 2, right? Then the probability of getting 2, okay, is going to be 1/3, right? That's the calculation which we do for each event. So this is kind of something which we calculate for an individual event. Now, what happens when, let's say, there is some event which is dependent on another event, or in other words, I should not use that word, let's say, dependent. Rather, what I should use is that I should use the word like because of one event, the other event may happen. Okay, or those two events are somehow linked with each other. They may not be related, but they are linked to each other. Okay? For example, what happens that I want to play? Okay, what is the probability that I would like to play? I would like to go outside and play, provided provided the temperature outside is low, it is actually raining, okay, there is some wind which is blowing, okay, and the outlook is also, let's say, humid, right? So what we are doing over here specifically is that I'm trying to ascertain what is going to be the value of my target, or what is going to be the target outcome. Okay, what is going to be my target outcome given a set of features. So I have a set of features, right? What can I do, or how can I model the probabilistic relationships between the feature and the target, right? So this is how conditional probability is given. Okay, this is how conditional probability is really written down. How it is really written down is that, let's say I have one event, okay, which has already happened. In this case, let's say event B has already happened, and I want to know if A will happen after that or not, or because of that or not. So is there any probabilistic dependency between A and B, right? So what I'm saying is, let's say B here is whether there is rain outside or not, right? Then will I be able to play or not, right? Then in that case, play will be given by the variable A, the random variable A, and random variable B refers to whether it is raining outside or not, right? So this is a very simplistic kind of an implementation where Bayes theorem comes to help, and it says, okay, that I can model this probability relationship, Okay, I can model this probability relationship stating that the probability is as simple as happening of B if A has already happened, provided I can get this information. I have to get that info. Okay, multiplied by class prior, or otherwise known as P of A. I'm going to define what is class prior. Okay, divided by, okay, probability of B, which is known as the predictor prior. And this value P of B given A is also known as likelihood. Now, what do I mean by all these terms? So first of all, what I'm trying to find over here is an event A, or the chance of happening one event A when B has already happened, which means I'm looking into something in the futuristic view, right? So that's the reason why this value or this calculation is, or this probability is also known as a posterior probability. Okay. The denominator over here is probability of B. Now, obviously, the example which I took over here clearly states that if B, in this case, if A is whether I'm going to play or not play, and B is going to be the weather outside, then weather becomes my feature and A becomes my target. So B is my feature variable, A is my target variable. And that's the reason why this is a predictor probability, right? Because we have another name for feature variables, which is the predictor variable. So that's why I'm calling it predictor probability. But why am I calling predictor prior? Okay, predictor prior is because I'm already aware, or I need to be aware of this probability before even I calculate this value, right? Because as per the formula, I need to divide something by P of B, by the probability of B, which means I need to know the value of PB, right? P of B value is something which I need to know, right? Which I need to know a priori, which I need to know previously or beforehand. And that's the reason why a synonym word called prior is used over here, right? And again, if B is my feature and A is my target, so probability of B becomes predictor prior. If probability of B becomes predictor prior probability, then P of A becomes my class prior probability, right? That's the reason why P of A is known as class prior probability, because A is my class and I need to already know what is going to happen, or what will be the probability of A happening, right? Right, and that is the reason why it is known as a prior, right? Now, what is this one called about? This thing is also known as a likelihood. Okay, this thing is also known as a likelihood. Okay, a likelihood is as simple as a function. Okay, a function, or otherwise known as likelihood only, which tries to okay, which tries to model any probability density function. This is the textbook kind of a definition. If there is any function by means of which I can understand the probability density function, okay, then that function becomes my likelihood function, or it is otherwise known as likelihood. Now, there are many kind of likelihood functions like maximum likelihood, okay, log likelihood, and so on. So we are not going to go into those many details because they are not required in our context to understand naive Bayes. But as of now, what we should be interested in is the likelihood of the opposite. Okay, similar to what we used to do in case of null hypothesis and alternate hypothesis. So this is not to be confused with null or alternate hypothesis, but this is just a way to understand it. That is, P A given B is my null hypothesis or my alternate hypothesis. Okay. So let's say P A given B is my alternate hypothesis. Then my null hypothesis becomes P B given A, because it is the mirror image. It is just the opposite, right? Now, what or why we are trying to find out the likelihood is because Bayes' theorem states that any conditional probability statement, when the outcome is dependent probabilistically on some features, then it can be modeled as likelihood multiplied by class prior, and the entire function, the entire outcome can be divided by the predictor prior. Right? Then we are going to get the conditional probability of any event A, or the chances of an event A happening given B has already happened. Right? So this is the basis that we are going to take during the entire class, and we will try to understand what is really going on here. Okay, this is the basis which we are going to take, and then we are going to understand what is going on here. But to understand this really well, let's take an example. If I take an example, that will be clear. But before I even take an example, let me just write this down. Okay, that my base theorem. Okay, so I'm going to convert this cell into a notebook. The knife base algorithm is basis the base theorem implementation, assuming okay, assuming the features are always independent, right? They are entirely independent with each other. That's the reason why our algorithm is called naive based, because that is a very naive assumption that my features will be uncorrelated with each other, which in real life is a very, very difficult thing to find, because whenever we start collecting features, we will always find, okay, we will always find that there is, I will not say any mistake, because that is not really our mistake that one feature is related to another. We already know from statistics that we may not even find variables which are related, which are otherwise known as the confounding variables. But there will always be scenarios where one feature is related to the other is related to something else. And that is how the data comes to us, or that is how we are able to collect the real life data. It is quite obvious that all of the problems, many of the problems are going to have intercorrelated features. But then it is our duty to get rid of that intercorrelation, because naive Bayes will only work brilliantly if I don't have any interdependency between the features, right? If I have an interdependency between the features, my algorithm is not going to work. The second point here is Bayes theorem can be mathematically given as uh, as I wrote, probability of any event A happening given B has already happened. Okay, so this is given as in the denominator. I'm going to say uh, the likelihood, which is probability of B happening given A. Okay, multiplied by the class probability, which in this case is P of A. Right, I'm just going to give a space over here just to avoid any confusions. And then in the denominator, I'm going to have the predictor prior, right? In the denominator, I'm going to have the predictor prior. So if I'm able to model my problem in this way, then I should be able to use naive Bayes. Now, naive Bayes being such a generic used kind of an algorithm, probabilistically we can model any outcome, right? In the entire world, we can probabilistically model any outcome, especially my classification problems is where I can really model things in terms of the probability. That's the reason why naive Bayes has broad variety of uses. Broad. There is no reason why in some cases naive Bayes cannot be used. So in almost all of the classification problems, you will find that naive Bayes cannot be used. And this is also directly descending from the Bayes theorem also, because since Bayes theorem uh, models the conditional probability, which is which is the most which is the most prominent, I will say, prominently found, or it's kind of a profound, prominently found naturally occurring scenario, because any naturally occurring scenario is where you will find something has already happened. That's the reason why something else is being felt. For example, it is really cold here in the city where I am, right? Because it is cold, I am actually wearing a sweater, right? So even simple things like this can be modeled using conditional probability. So since Bayes theorem or conditional probability is generic in nature, hence naive Bayes, okay, naive Bayes algorithm also finds its use in any such naturally occurring situations. Okay, but predominantly, I have seen in the industry that they are mostly used in the banking kind of domains, or wherever probabilistic natures are really to be taken care of, or maybe in healthcare and so on and so forth. Right? But that does not mean that the rest of the industries do not use it or cannot use them. Okay, almost all of the industries use this. The only thing you have to take care of is your data should not have any multi-collinearity problem. Let's take an example and we'll try to understand what is really happening here. Okay, we will take a quick example. I'm not going to write that as notes, but that example will be simple enough for us to understand what is going on, right? So until this point in time, you have any doubts there, Rohit?
No questions.
Okay, okay, thanks, Rohit. I hope you can still see the Jupyter notebook and the blank cells, right?
Yeah, I can see it.
Okay, okay, great. So let me take my pen once more, and then I'm going to explain one new use case. The new use case is, let's say, I'm going to ask a simple question given a scenario. So I'm taking a scenario first, and then I'm going to put forward a question, and then I'm going to solve that question. So the scenario is that, let's say I am running a manufacturing unit. Okay, I have a factory where I have two machines. Okay, I have only two machines, M1 and M2. Okay, now I am using this factory of mine. This is where I'm actually producing light bulbs. Okay, I'm actually producing light bulbs, and what I'm seeing is this machine M1 can produce, let's say, okay, on an average 30 bulbs per hour. Okay, so per hour I'm able to produce 30 bulbs. Then the machine number two is producing 20 bulbs per hour. Okay, it is a bit less in count, but both the machines are actually performing like this. I have only two machines only. So in an hour, how many am I doing? 50, right? In an hour, I'm doing, let's say, 50, right? So in an hour, in total, I'm doing only 50 bulbs, right? Now, obviously, I'm not working for 24 hours. Obviously, these two machines are run by some people. These two machines are not so automated that they run by themselves, right? So I already have people who are running machines M1 and M2, right? Now, what I'm seeing is that, okay, now what I'm seeing is that over a period of time, there is one more engineer which I have whom I have appointed as my quality control engineer. The quality control engineer checks for the uh, uh, productions of these 50 bulbs, and he's going to validate whether the bulb is good or bad. What he tells me in almost every weekly report, right? He sends me a report every week. Okay, every week, what he's telling me that 1% of my bulbs, okay, 1% of my bulbs are always faulty. Okay, 1% of the bulbs that I really produce are always faulty, right? Which means in a day, if let's say I'm working for 8 hours, if my factory is running for let's say 10 hours, so 50 multiplied by 10. Okay, so for 10 hours, I have run the emissions through and through. Then there are 500 bulbs which I have really produced, assuming I have not given the machines any break. So 10 hours straight they have run, 500 bulbs they have created. Okay, I am quite certain that my QA engineer or my quality control engineer is going to report five of the bulbs are actually faulty because 1% of the bulbs are entirely faulty. This is what he's saying, right? So, however, when I ask him which machine is more faulty, right? Because I have only two machines. You tell me the machine name, I'm going to fix it. He is telling me that both the machines, M1 and M2, are equally responsible for this 1%, which means these five bulbs which are coming out every day, okay, there's a 50% chance it will come out of machine number one, and there is a 50% chance it is going to come out of machine number two. Okay, just like tossing a coin. Okay, tossing a fair coin, there's a 50% chance that I will get a head and 50% chance I'm going to get a tail. In the same way, my quality control engineer is saying that, sir, 1% fault is fine, but both machines are equally responsible. So I cannot really tell you which machine is at fault. Right now, I ask the question. So this is the scenario. Now I'm going to ask the question. The question that I'm asking that given I have a bulb, let's say this is my bulb, and that bulb is let's say produced by machine M2. I have bulb M2 or machine M2 which is producing this bulb. What is the probability that it is faulty? So what is the probability that it is faulty? Now, why did I take machine M2? Because I'm suspecting it might be because of M2 because already its production rate is lower. Maybe it is faulty already. I have some kind of null hypothesis going on in my mind. I'm not able to trust the machine number two, or maybe the person who is operating machine number two is very lazy and he's not checking the machine from time to time. He's not maintaining it really well, and that's why there can be a very high chance of it giving me error. So that's why I'm saying that I'm trying to understand, or you tell me, or being a data analyst, you tell me what is the probability So what is the probability of a bulb being defective? Okay, a bulb being defective given it is produced by machine number 2. So clearly this is a conditional probability problem. If I try to use Bayes theorem, what am I going to do? I'm going to simply put this as m2 given d, right? M2 given d is going to be my likelihood multiplied by the class prior. Class prior here is going to be p of d, right? And then I'm going to divide this by p of m2, right? Now, how do I calculate these things? Is what is the algorithm itself, right? What is the algorithm itself? So, if I understand how this is calculated in this kind of a question, this kind of scenario, then I will be able to understand how naive Bayes algorithm works, right? Now, considering that in mind, I'm just going to remove a few things from here. I hope you got the question there, Ruhi, right? You got the question there, right?
Yeah, yeah,
Yeah.
I got
The question is clear. The scenario is here. Let's try to see what we can do. So, whenever we are given a question like this, the first thing that my algorithm does, the first thing that I need to do is to calculate all the given information in terms of it's a probability. I have to model everything in terms of the probability factor. So, for example, what all things are already given? I am already given what is the probability of a bulb getting produced by machine number M1. And that is, if I only take 1 hour of the production, that will be equal to 30 by 50 because 1 hour it is producing 30, total is going to be 50. 30 is my favorable outcome, 50 is the total outcome. Hence, the answer is going to be 0.6, right? Obviously, if this is 0.6, probability of M1 is 0.6, then probability of M2 is what? 0.4, right? Because I have only two machines, right? You can also verify this probability of M2 is going to be 20 divided by 50, that will be equal to 0.4, right? If that is the case, right? If that is the case, then what is the probability of a bulb being, it's a defective? Probability of a bulb being defective is only 1%, which means it is equal to 0.01. Now, when I asked my QA engineer what is the chance or who is really responsible for this 1% defective item, he said both machines are equally responsible, right? He said both machines are equally responsible, which means what? Probability, right? Okay, of getting a defective item given it was produced by machine number M1 is equal to probability of getting a defective bulb given it was produced by machine number 2, and both of them are equal to 50%, so I can write them as 0.5, right? Both of them I can write it as 0.5 because this information is already given to me. My data set already gives me this information. My QA engineer has already given me. Then I can simply take this value, right? This value, right? And this value in this case, and I can put it into this equation, right? I can simply replace P of M2 given D as 0.5. So this equation becomes 0.5. Okay, in the numerator, I'm going to have, let's say, 0.5 multiplied by probability of D. Probability of D is 0.01. Okay, divided by the probability of M2, which is equal to 0.4. So I'm just going to put it over here, right? If I simply put that thing over here, right, I can do a calculation here and I can find out that this value, right, is going to come out to be equal to approximately 0.0125. Or if I convert this into percentage, this is going to come out as what? 1.25. So there's a 1.25 percentage chance that the bulb which is produced by machine M2 is a defective bulb. In the same way, I can also calculate probability of a defective bulb produced by machine M1, right? What is the total chances of a bulb being, it's a defective given it is produced by M1? So in that case, what is going to happen? The numerator is going to remain the same, right? The numerator is going to remain the same. Only the denominator is going to change. The denominator is going to become 0.6, right? So if I calculate this, it is going to come out something like, if I'm not wrong, 0.0083, right? If it is equal to 0.0083, then this value comes out to be 0.83 percentage. So there is only a 0.83% of chance, 0.83% of chance that M1 is going to produce a bulb which is a defective bulb, and there's a 1.25% chance where M2 is going to produce a defective bulb. Hence, my null hypothesis that there is something wrong with M2 cannot be rejected, right? Right, in terms of the hypothesis testing kind of a world, I cannot really reject my original assumption that there is something wrong with M2, or the person who is running the machine M2 is not doing it in an efficient way, right? This is the way we calculate the conditional probability, right? This is the way we entirely calculate the conditional probability related things. Now let's see what my algorithm is going to do. Okay, what my algorithm is going to do, considering I understand what has happened right now. So clearly, I need to know all the prior. So I am just going to write this over here. As much as possible, I need to know all the prior probabilities, right? So that I can solve our equation and find the answer, right? I need to know all the prior probabilities so that I can answer the above question, right? Now let's see what Mr. Naive Bayes is going to do. So algorithm. Okay, the steps which are followed in the algorithm is such that first step, Naive Bayes will read and understand the classes in the data. Okay, this is where it understands whether it is a single, it is a binary class or a multi-class problem, right? So it is something like I'm trying to draw a scatter plot. Okay, I'm trying to draw a 2D scatter plot where x-axis has feature 1, y-axis has feature 2, and basis those two features, I'm just trying to figure out the distribution of the data, right? So let's take a quick example also. Let's say I have two classes of data. I have, just for the sake of simplicity, I have two classes of data. I have total, let's say 26 points. Let's say I have 26 points in my data. One of the class is this. This is, let's say, class 1, and it has more values. So let's say 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So let's say 16. So this cross marks belongs to class level 1, and let's say this 0 mark will belong to class level 2, right? And 0 mark has only 10 data, obviously, because I have 26 observations, right? So I'm just going to draw the rest of the 10 observations here, right? So I have 26 points. Class 1 has 16 points. Class 2 has only 10 points. It's not a very imbalanced kind of a data, but let's say this is the scenario. Now, this is what my first step will be. So the algorithm is just going to understand what the data distribution is, right? Once it has understood what it is going to do, the second step, okay, is as simple as it is going to expect a query point. So given a new or unknown point or unknown point, the model will now try to understand which class it belongs to. This is the probability calculations, right? Now what it is going to do, once you have already provided that, let's say, data point, okay, once you have already provided the data point, what it is that it is in exactly trying to find, it is exactly trying to find, let's say, what is the probability, okay, given any unknown point x, that it belongs to, let's say, class 1, right? Or it belongs to class 2, right? It belongs to class 2 given any query point x. So if I just ignore the second line, I'm just going to concentrate on one so that I can write the formula. So if I'm going to only concentrate on the first one, obviously you would have already understood what the answer is going to be. X given 1 multiplied by probability of class 1, okay, divided by what? Divided by the probability of x. No, yes, yes, true, right? So x is my feature, right? The x is my features here. One is my target, and x given 1 is my likelihood. right? I just have to calculate this. So how do I calculate this? In the other example of machines M1 and M2, I gave you a lot of information so that I can understand how Bayes theorem or Bayes equation can be solved. But in this case, I just have 26 points, 16 with one class, 10 with the other class. And let's say, just for the sake of drawing this, let's say this is that unknown point. This point that I have drawn is that unknown point. Now, how will that algorithm work? Okay, how will it know how to calculate the priors? Because without calculating the prior probability, right, it's not going to do anything, right? I cannot do anything without calculating the priors. One thing it can really calculate is that from the given information, what it can really calculate, okay, is that it can calculate what is the probability of one, right? Probability of one it can really calculate because I have 16 favorable outcomes out of 26. So probability of one becomes, or probability of class one becomes 16 given the 26, right? So approximately this will be how much? 16 divided by 26, something like 0.61 or 62 something, right? I think it will be something related to 0.61 or 0.62. Okay, somewhat closer to this, right? So uh, I have got at least one answer. Okay, I don't know the rest. Now, how am I going to calculate the rest? Okay, let's see. Okay, what the algorithm is now going to do is that it has got the probability of one class. Now it is going to calculate the p of x. Okay, now it will try to calculate the p of x. It is going to calculate the denominator. And to calculate the denominator, it is going to take a root. It's going to take a technique which is approximately similar to what we used to do in KNN, but there is a fundamental, it's a difference. Okay, what it is going to do is that it is going to draw a virtual circle like this. Let me just do one thing. Let me draw that virtual circle in a different, let's say, color. It's going to draw a virtual circle like this. Okay, how does it draw a virtual circle like this? This is a parameter which you can pass in the algorithm. Okay, where you can specify the number of values, the number of nearby points, the number of values it is going to constitute. If you pass the value is equal to 3, it's going to create a circle which takes in 3 nearby values other than the query point. So query point is there already. Other than the query point, it will take 3 more points. Right? Now see what is really happening here. Okay, see what is really happening here. It has drawn a circle. So let me just write it down. Around the query point, my algorithm will draw a virtual, okay, circle, okay, with k number of points, not to be confused with k nearest neighbor, but it is a value which is a prior value, okay, prior value that we can provide in our model itself if we want to, or otherwise it takes a random value, right? It can take a random value also. In that case also it is going to perform quite well, right? What it is going to do now after it has drawn the circle, that virtual circle it has drawn, what it is going to do inside that circle, okay, inside that circle it is going to do some calculations to find the p of x. Okay, to find p of x it is going to do some calculations inside the circle, right? So what the calculation is that going to do? Within the circle, my algo tries to find, okay, it is going to try to find p of x by, it is going to find how many, right, how many points excluding the query point, excluding the test point or my query point, okay, are present. So clearly how many points are there inside the circle other than my point. Okay, so in this case, how will that be? So I think I have not really written over here point number. Uh, this should be 4. This should be 5. Why is that going to be 4? Is that we calculated P of class 1, right? So now we calculate P of class 1 and P of class 2. Okay, as 16 by 26. P of class 1 is going to be 16 by 26 and 10 by 26, right? Let me just open the calculator and let me quickly do the calculations. You may not be able to see that on my screen. Let me just do that. 16 divided by 26 is 0.62 and 10 divided by 26 is 0.38. So which is 0.62 and 0.38, right? So P of class 1 is 0.62 and P of class 2, obviously I didn't have to calculate that because the probabilities are going to sum up to 1. So P of class 1 is 0.62, P of class 2 is 0.38. So I'm just going to mark this in bold, right? So this is what it has already calculated. Now it is going to draw a virtual circle with k number of points, not to be confused with kn, but it's a value which is a prior value that we can provide in the model itself. Else, it is chosen randomly, even in which case the algo works very well. Okay, we will come to know why it really does that when we are done with the calculations. Now within the circle, our algo, okay, our naive Bayes algo tries to find how many points excluding the query points are really present. This becomes my P of x. Okay, the probability of x or the probability of my query point becomes what? How many points, okay, are there, number of the observations which are there inside the circle, which it is considering as number of similar observations. Okay, so it is considering them as number of similar observations within the circle, right? Observations within the circle divided by the total observations. Okay, so if you look at the circle, how many points are there inside the circle other than the query point? 3 points are there, one cross is there, two circles are there. So I'm going to say 3 divided by 16. And 3 divided by 16, let me use my calculator. This is going to be 0.12, right? 3 divided by 16 is going to be 0.12. So this is going to be my P of x, right? So my P of x is done. Okay, now what I need to do, I have P of 1, I have P of x. Now I need to calculate Px given 1. So if I want to calculate Px given 1, right, how can I do? Now I again look inside the circle. Okay, again to calculate the likelihood function or outcome, we check inside the circle, okay, for the occurrences of our class value. So if we are talking about probability of class 1 given x, then we are looking at how many numbers are there inside this circle which is for class 1, or how many numbers are there for class 2. So let's say in this case, how many numbers are there for class 1? Only one, right? So I have P of class 1 given x, right, is equal to number of points of class 1 items inside the circle. So number of class 1 items inside the circle, right, that will be divided by, that will be divided by the total number of points. Okay, that will be divided by, give me just 1 minute, that will be divided by the total number of points in class 1, right, which is equal to, there is only 1 point of class 1 here, right, 1 divided by 16, right, this is going to be equal to 1 divided by 16. Okay, what is going to be 1 divided by 16? Where is my calculator? 1 minute. I think I closed it. Let me just open 1 divided by 16. This is equal to 0.063. Okay, or 0.06, I'm going to say. Okay, I'm just going to round it to 2 places. All right. Is let me know, Rohi, if you find any of the calculations are going wrong. Maybe you can also use a calculator from your side and try to see if there are any calculations which has gone wrong. Okay, because if we do anything wrong over here, the formula, the final output is also going to be wrong. Now we can calculate the final probability, which is nothing but, okay, I'm going to calculate what? P of, okay, class 1. Probability of getting class 1 given my query point, which is equal to what? A numerator by the denominator. In the denominator, I'll have P of x. What is P of x? 0.12. And in the numerator, I'm going to have P of x given 1, which is 0.06 multiplied by, it will be probability of 1, which is 0.62, right? So if I do this calculation, let me just see what this answer comes out to be. Okay, 0.06 multiplied by 0.62 divided by 0.12. Right? This comes out to be 0.31 approximately. Approximately 0.31. So clearly, if this is 0.31, clearly, if this is 0.31, then what I can say is I can simply take this mm, area from here and I can put it over here. Probability of the point falling into class 2 is what? If this is 0.31, then 1 minus 0.31, right? 1 minus 0.31, which should be equal to 0.69. Right? So this is the calculation that we're doing over here. Now, clearly, you can see that this is quite valid also intuitionally, because within the circle, I have 2 points which belongs to class 2 and only 1 point which belongs to class 1. This is where many of us get confused that this is like a k nearest neighbor kind of a thing which is going on, but the calculations are entirely probabilistic. And the circle or the items which are contained within that circle is a hyper parameter also, which I'm going to pass, right? The value that I'm actually passing, I'm going to define what is going to be the value. Basis with the circle will be drawn, and then all the calculations are going to happen. So I'm going to calculate probability of each classes, right? Then I'm going to calculate probability of x by drawing that virtual cycle, right? I'm going to draw the virtual circle with k number of points, right? Number of similar observations within the circle. How many observations are there similar to the query point? Now, when the query point is not classified, everything else is similar to the query point only. So that's why I have 3 points. This is 3 given by the total number of points, which is equal to 26, right? So 3 divided by 26, I'm going to get a value 0.12. Then I calculate the probability of class 1 given x, which is my likelihood, right? Which is my likelihood, which is going to be how many class 1 items are there? Only one item is there within the circle, given the total number of class 1 items, which is 16. Hence, 1 divided by 16 is equal to 0.06. Now, I can calculate a final probability given the formula. This is just a copy paste of the Bayesian formula, right? I'm simply putting the Bayes theorem here and I'm calculating probability of 1 class. Obviously, this is a binary class kind of a problem, right? It is a binary class kind of problem. I have two classes, 1 or 0. Probability should be summing up to 1. Hence, the probability of class 2 is going to be 0.69. Right? This is the way the algorithm works. Clearly, there is one dissimilarity between KNN and I base. The circle does not come out of any nearby neighbors and so on and so forth. But there is one similarity also. Similarity is other than point number 1. There is nothing which I have done in what? The training set. In the training set, or in the training stage, I've only done point number 1. Everything else is done during the testing stage, right? In that case, you might wonder then it should be as slow as KNN, but it's not, because in KNN, you have to calculate the distance, right? In KNN, we have to calculate the distance basis. Let's say if we are using, let's say, Minkowski, then depending on the value of P, it's going to change. But in this case, my calculations are very simple because it is really probabilistic. And all I'm doing is, let's say, divisions and the multiplications. I'm only doing, let's say, divisions until this time, until this time, until this time, right? And then finally, I'm doing a multiplication and a division. So the time or space complexity is really very, very small in this case as compared to any other calculation, right? You try to compare this with the decision tree. For each and every node split, I have to calculate information gain and entropy and so on and so forth, and go ahead. Right? In case of KNN, for each and every distance, I have to calculate, then I have to sort and so on and so forth. It depends on the number of the data points also. But here, what I have done, I have restricted myself to the virtual circle. So I'm only looking inside the virtual circle, hence my number of points are also going to be restricted to that number. Hence, this will be much faster, right, as compared to any other algorithm. I hope it is clear.
Yeah, it's clear. But I have a question.
Yes, yes.
So you're saying that we will pass the value of k and then we will have multiple answers. So
Yeah,
how
we
are we
may
going
want to.
to,
Yeah.
yeah, so how we are going to decide which one is better?
We can actually decide basis the grid search cross validation kind of thing, right? We can do that using grid search cross validation kind of thing. So if I look at naive Bayes, this is a Gaussian naive Bayes kind of a calculation. Gaussian naive Bayes, I have actually deliberately taken Gaussian naive Bayes. Naive Bayes has many other ways in which naive Bayes can be implemented in sklearn, but here you see the priors, right? So the priors are actually where it is already calculating this, right? In some cases, let's say in case of sklearn, it is not even giving you the option to change it, right? It specifies only the hyperparameter which you have, right? Is the specification of the priors of the classes, prior probability of the classes. Okay, this is the only thing that you can pass. Sklearn does not even expect you to pass the value of k. It is automatically calculated by sklearn by a random value. So depending on your size of the data, it is going to take a random value, right? But that is not really going to matter because that random value, first of all, will be selected very small, and hence the smaller area out of a bigger data set will be selected. Hence the computation time will be small, right? And then, irrespective of how many points are there, right? Irrespective of how many points are there, the final calculations may not really change because it is actually looking at the affinity of the points within the circle. Are you getting my point? So it is looking at the affinity within the circle. So howsoever big or howsoever small it is really not going to matter. However, sklearn already does this in a very, very efficient way in the backend. It's already there in the documentation if you would like to read how it is really implementing it. But it uses a very, very less value or a small kind of a value, which has been it's a suggested out of multiple trials and errors on the algorithm itself.
Okay.
Okay.
Okay, so also like in the diagram you showed, the point will be selected in the between of those classes only, or
No,
it
no, no, no.
can,
No, that can be anywhere. I mean, in my example, it was there. Now, it is a test point, right? In my example, what I did, let me take a very
yeah,
simple case.
yeah, because if the point is shifted to either of the sides, then the area will change and the calculations will change
Right, it has to
drastically.
increase,
Yeah.
right? The area has to increase, right? In that case, what I need to do, if my point is going to fall over here, I have to scale my data. If I scale my data, if I have scaled my training and my testing data, then their ranges will be constrained. So that is the reason why one of the things which we do in case of naive Bayes is that we scale the data so that this point which was falling like this should now be falling somewhere here,
Okay. Okay.
right? Then creating the circle will be easy. Now it can create a circle quite easily. Let's say it is going to create a circle like this. And then by creating a circle like this, it is going to calculate the PFX. Obviously, because this point is very closer to the 0 point, it is going to calculate it. But KNN is not a place that you have asked, which is a very valid kind of a question. Let's say, because of whatsoever reason, even after scaling or even after whatsoever you do, you have a valid case of an outlier, right? You have a valid case of an outlier which is falling here, right? In that case, KNN or in that case, naive Bayes is going to be confused, right? So the if there will be impact. So presence of an outlier is going to drag the model. It's going to make the model worse. So we have to take care of the outliers. Either we have to drop them or we have to scale the data so that it fits within the range of the data.
Okay.
Yeah.
Okay, okay. Also, in this algorithm, point 6 and 7 are both calculating b of class 1 by x. I think
No,
in
no, no,
point
no. Sorry,
6.
sorry. That is actually my
Yeah,
mistake. Let me just clear it. This is x given class 1.
yeah.
This
That's
is
what I was
x
listening.
given class
Yeah,
1. Let me just delete this. This will be x given class 1.
yeah. No more questions now.
Okay, Rohit. In the interest of time, let's stop here. But I'm just going to quickly show you what data we are going to use. We will use that credit card default thing. I just downloaded this data. There is an ID column which we can get rid of. We will use the rest of the columns, but obviously we have to take care of two things, which we are going to do by tomorrow, right? So we are going to take care of. Let me just write assumptions. Okay, these assumptions will be applicable in case of practical implementation also. No collinearity, and no outliers, right? We just have to make sure that there is no multicollinearity, there is no outlier. If I have, let's say, multicollinearity, what am I going to do? I'm going to remove them. Okay, but because I am not training or finding the patterns during training, like I was doing in case of, let's say, decision tree. In sklearn, if you go to the documentation, you will not find, okay, any attribute, right? Any attribute or any function, okay, any method which is giving you the coefficients, okay, which is giving you the coefficients for the features. In other words, this kind of a lazy learner, because it is a lazy learner, right? Everything is done on the testing data itself. There is no way to find out the coefficient of the features, because the coefficients of the features are in this case irrelevant. Same is the case with KNN. Hence, we will not be able to use methods like RFE or VIF, because RFE or variance illusion factor or recursive feature elimination, their baseline is to use the coefficients. They use the coefficients to reverse engineer their value, right? In other words, they will see the goodness of it and reverse engineer their own value, so that I can get a list of that VIF pandas, a data frame which we created earlier also, right? So we will get a data frame where we are going to have the feature name and the VIF score or the RFE score. We cannot do that here. So how do we get rid of multicollinearity is going to be a completely subjective task. Okay, it is going to be a completely subjective task. We have to look into the correlation metrics, and we have to get rid of the variables which we believe are not contributing as per our business use case. Okay, there is no mathematical way to get rid of the columns. Are you getting my point? So because
Yeah,
it
yeah.
is not fitting any straight line or something like that, there is no question of any coefficients, right? Okay, Rohit. Then for the sake of time, let's close for the day. We are going to continue tomorrow. Is that fine?
Yeah, okay, sure.
Yeah. Okay. Thank you, Rohit. Thank you
Thank
for
you.
joining.
Good night.
Thank you. Good night.